I'm a little bit behind, so I thought I'd get up this morning and record some podcasts. So I'm trying to get ahead. Get it? Get ahead, right? Because my head's so small, right? Nothing. Okay. All right, podcast 2.2. Hess's Law. Hess's Law is named for Mr. Hess, the guy who worked on thermodynamics. So basically what it says is it doesn't matter whether you do it all in one fell swoop or if you break it up into a series of steps. The change in enthalpy, remember, that's the loss or gain of heat. The change of heat is the same. Going back to the betting thing. If you win $10 in one bet and you win $10 in another bet and you win $100 in another bet, all of a sudden you're up what? $120? Well, if you had just placed a bet for $120 and won, you'd be up $120. So it doesn't matter if you break a system down into 2 or 3 steps, or if you just break it down into one step. Well, that's not really breaking it down, but the change in enthalpy is the same, mainly because of the first law of thermodynamics. You can't lose heat along the way. It's not like if you break it up into steps, it's less efficient, and so some heat just gets lost. Here is, on the right-hand side, if you guys look at this, a chemical reaction where we are changing N2 and O2 into NO2. So N and U make no, right? The delta H for that is 68 kilojoules. That is a one-step reaction. Bring it over here to the left, and what you see is the same reaction, but N2 and O2 makes O2 and 2NO. In other words, we're taking one of the N2s and one of the O2s, and we're combining them, which gives us an O2 left over. So the intermediate step is we make NO. So we're left with no. Get it? No. 2 no's. Still nothing? Really? That's bad. That reaction right there takes in 180 kilojoules. That actually absorbs 180 kilojoules. So that'll be plus 180 kilojoules, right? So the second reaction, when we take NO and mix it with O2, loses 112 kilojoules. So if you're up 180 and then you're down 112, what is the net effect of that? The net effect of that is right there, positive 68 kilojoules. That is Hess's law. We will want to calculate the enthalpy of a reaction in AP chemistry using Hess's law. So what you're able to do is you can multiply any equation by a number if you need to make things work. You can also flip any equation that you need to make things work, right? So in this equation right here, let's say I had to flip. The N2 and O2 makes 2NO. So basically the reactants become products, the products become reactants. If I had to flip it in order to make things work, I would just flip the sign. And that makes sense because if one reaction takes in energy, then the reverse reaction should let go the same amount of energy. If you have to multiply an equation by anything, you just multiply the delta H by that same number. So down here on the bottom, we took that 180 and we multiplied it by 3. And we also multiplied the entire equation by 3, right? So let's look at an example and see what we would do. Thermite is an awesome stuff that involves aluminum and iron 3 oxide. And I'll show you all this in class if I haven't already. The equation looks something like this, right? It's just a redox reaction. We're just trading the oxygens from the iron over to the aluminum. So here's one equation that we can look up. Al plus O2 makes Al2O3. Notice that there are fractions in front of it. That's okay. The idea is we only want to make 1 mole of Al2O3. And because of that, we'll want to look at it and go, all right, what's the way to balance it? So that's why they use fractions there. Don't let fractions throw you. Here's the equation for the iron. So the question is, how do you take these two reactions down here and combine them to produce this reaction up here? So first of all, you have to decide which one are you going to flip. Well, this equation right here looks okay because it's got aluminum on the left-hand side, and my target equation up here has aluminum on the left-hand side. The bottom equation with just the iron, that one looks like we have to flip it. So we'll flip it. The other thing you guys need to realize is this thing is not balanced. The equation in the top is not balanced. So before you guys can start doing these, you're going to have to go, wait a minute. Before I start flipping and doing all those kinds of things, let me go ahead and balance the equation. So you'll flip one of them, and then once you flip them, you just add them together. So I'm going to flip the bottom one. That negative 826 becomes positive 826. And then when I add them together, the oxygens cancel, and you get the target equation up top. That's what Hess's law says. You can add equations together to find the delta H. Here's another one. The bombardier beetle has two liquids, and those two liquids are hydrogen peroxide and hydroquinone. So here's the equations. That's our target equation right there. So go ahead and write down this equation if you would. That's our target right there. That's what we want to make. And then over here, these are the equations that you can use. So what I want you to do is just look at the target equation, look at these equations. You're allowed to flip any equation, and you're allowed to multiply any equation by an integer so that they all add up to your target equation. Right? So just give it a try. When you come into class tomorrow, we're going to practice a bunch of these, but it's more like a puzzle than math. The idea is, which ones do you want to keep? Which ones do you want to flip? And then do you need to multiply any of them by an integer? So give it a try and bring it in tomorrow. All right, there is a second way of calculating changes of enthalpy or delta H. It's called a cheater's way. Standard enthalpies of formation means how do you make something out of its basic elements? So we can take each individual compound and say how much energy does it take to make that. So as long as you understand what standard state is based on these notes, the gas has got to be 1 atmosphere, a solution is 1 molar, and the element is whatever it would be under those standard conditions, 1 atmosphere and 25 degrees. If it's nitrogen, it's got to be a gas because that's what form it is. You can make liquid nitrogen, but you couldn't use it for standard states because that's not its standard state of matter. All right, so this is the second idea of Hess's law. So to do standard heats of formation, here's what you can do. To find the delta H for a reaction, change of enthalpy, we're going to take the heats of formation, that's what this means right here, of all the products, and we're going to add them up. That's what that little sigma thing means. And we're going to subtract all the heats of formation of all the reactants. That's what this means over here. Now the N out front just means if you've got 2 of something in the equation, then you multiply that heat of formation by 2. So you would take all the products in the equation, you would add up their heats of formation, that would be given to you, and then you subtract what all the heats of formation of the reactants add up to be. Something y'all need to realize, see this little 0 up here, it looks like a degrees? That means just standard state. So anytime you see that little 0 on something, it just means this is the heat of formation, or this is what's going on during standard state. All right, just to wrap things up for chapter 6. All we want to know is delta H. That's all we want to know, really. So there's 4 ways to do that. Number 1, you could do calorimetry. Q equals MC delta T. You did that in chemistry 1. We'll do some in class. Not a big deal. The second one is Hess's law number 1, where you flip and multiply by something so that you can combine all the equations to meet the target equation. Number 3 is Hess's law number 2, which is heats of formation. They're given to you in a table, or you look them up, and you calculate the delta H based on heats of formation. That's all the products minus all the reactants. And then lastly is bond energies. We'll get to that in a little bit later in about chapter 8, but I just thought it was something that, try to calculate it, but I just thought you guys needed a big picture kind of a thing so that you would know where we were and kind of what the focus of this was. Thanks. See you later.